right, now that we've talked about the sources of acidity in soils, let's talk about the components of soil acidity specifically. So when we look at acidity in soils, where does that acidity basically end up? And so there's three ways to look at this. Total acidity, so how much acidity is present. And if you look at total acidity, it doesn't tell you the whole story of where acidity is present. And so total acidity is actually a function of two things, active acidity and potential acidity. Sometimes we call this reserve acidity, and oftentimes we call this buffer acidity. And we quantify this buffer often when we're looking at line recommendations, which we'll talk about in this unit. So this is what is meant by active acidity and buffer acidity, or potential or reserve. So active acidity is the acidity that we measure when we measure pH. We measure what you see in red. We measure the free hydrogen ions in the soil solution, and that's active acidity. The difference between active and buffer, or reserve or potential, is that potential or reserve or buffer, and maybe I should just say buffer because it's really buffer. I'll tell you why in a minute. But the buffer acidity is the acidity that's associated with two different things within soils. It's the acidity that's associated with clay particles, for example, hydrogen that's attracted to the negative charges on clays, and we'll revisit this negative charge concept on clays in the next unit. Regardless, clays are negatively charged and they attract positive charges like cations such as hydrogen, which is acidity, aluminum, which if this enters the soil solution, it can become acidic or create acidity. And so buffer acidity is the acidity that's on the exchange sites of clays, and it's also the acidity or the free hydrogen ions, well, they're not free yet, but hydrogen ions that could potentially become free from organic functional groups that are sticking out off of the edges of organic molecules or moieties. And so this is what happens. You want to change the pH of a soil. If you start removing some of the hydrogen ions from the soil solution, those hydrogen ions that are removed are buffered against change from the hydrogen ions that are stuck on the clay particles or on the edges of organic compounds. And so these are the reactions that occur. For example, if hydrogen just gets kicked off of a clay particle and is moved into the soil solution, it contributes to acidity. If aluminum, on the other hand, is kicked off the clay particle and enters the soil solution, it can react with water, undergo hydrolysis, the splitting of water, and form aluminum hydroxide compounds. And we've went through this cascade already in one of the previous videos where essentially three aluminums create three free hydrogen ions and generate acidity. The same thing holds true for these carboxylate groups or these alcoholic groups. When they enter into the soil solution, they can readily, depending on if hydrogen is removed from the soil solution, readily release hydrogen into the soil solution and buffer against the change in pH. So with that said, the components of soil acidity are simply two different pools. There is the active acidity, like we shared with you on the previous slide. Those are the hydrogen ions that are in the soil solution. And that quantity is relatively small compared to the buffer acidity or potential acidity. The active acidity is what we measure when we measure soil pH with a pH electrode and meter or a test strip. On the other hand, the potential acidity, which I really like to use the word buffer acidity, because this acidity buffers against the change in active acidity or pH of a soil. The buffer acidity is large. This buffer acidity contains hydrogen and aluminum and iron on the cation exchange sites. And we learned about what happens when hydrogen, aluminum, or iron are kicked off the exchange sites and either enter the soil solution or react with water to form 3 free hydrogen ions. We learned about that in one of the previous videos. Point number 2 is that this pool is large. It is way larger than the active acidity. And this pool buffers the change in soil pH. And so when you're trying to change the pH of a soil, which is what we will discuss in this unit, this potential acidity needs to be neutralized before the pH of a soil will actually change. And when we measure potential acidity, we don't do this with an electrode. We do this via titration. And I'll give you a rough example in one of the upcoming videos. So let me share with you one other concept about buffering capacity of soils. So the term buffer simply means a solution that resists change in pH. And we're going to learn about or relearn about cation exchange capacity in the next unit. But as cation exchange capacity increases in a soil, from soil to soil to soil, the buffering capacity increases. And that's because there's more places for hydrogen, aluminum, and iron to be attracted to in that particular soil or soils. And thus, what you're going to learn again or learn in this unit is the liming requirements necessary to change or remove the buffer pH or the buffer acidity, right? And those lime requirements increase as buffering capacity increases, i.e. as CEC or cation exchange capacity increases. And so here's an example and somewhat of a prelude to the next unit. So if you want to change the pH of a soil, which is what we're going to talk about in the next video, you add increasing amounts of lime and the soil pH on the y-axis will change. If you have a soil with a low cation exchange capacity, the pH of that soil as a function of increasing lime amount is going to change quickly. That's because it has a low buffering capacity, low cation exchange capacity. On the other hand, a soil with high cation exchange capacity is going to resist the change in pH. And so as you increase the amount of lime, you see very little change in pH. Of course, it will change, and but it doesn't change to the greatest extent as a soil with low cation exchange capacity. And I hope that makes sense, and we'll revisit this when we get into Unit 4.